Today we're talking about line integrals. And we're going to start today in just 2 dimensions, and everything we do is going to be easily extendable into R3 as we need it. But typically with a line integral, we're starting with 2 things that are going to be in our xy plane. So the first thing in our xy plane is going to be our curve C. And again, we're going to be looking at a specific interval from A to B, and of course, as always, the direction is going to be very, very important. The other piece is that we're going to be given some function f of xy, and again, typically equals z. Now again, that usually describes a function in 3 space, right? In R3, a 3-dimensional surface. But we're really just concerned about this part, right? Our domain. And we're basically going to be taking our domain in the xy plane and combining that with our function c. So every point in the xy plane is going to be equal to just one single value. And then again, we're going to be combining that with our curve c. So the way we define a line integral, obviously we're integrating, and we're integrating over our curve C, which is that very nice, neat, compact notation, right? Where am I integrating? Just on the curve C. So all I'm considering is every ordered pair along my curve C. What am I doing? Well, I'm going to plug in every single ordered pair of that curve C into my function f of xy, which again is just going to give me a value. And then I'm going to multiply it by these tiny little chunks of arc lengths, or my ds. Basically, we're going to be integrating with respect to ds at first, which means, again, as we take my arc, or my curve C, we break it up into our tiny little chunks of ds. Inside each little chunk, we're going to consider a point P. That point P is going to be in terms of xy, and we're going to plug that into my function. Multiply it times my tiny little arc length, sum all of those, and that gives me my definition of a line integral. So now let's look at a few quick examples of what we're actually doing when we compute a line integral. Alright, so time for our first example. Now, I'm about to do 3 examples in a row, and don't worry so much about trying to necessarily write down as I'm doing the whole problem. For these first 3 examples, I really just want you to listen. Just watch what I'm doing, try to follow along, try to see if you understand what it is that I'm actually doing, instead of trying to write down at the same time. Typically, most of your examples aren't going to necessarily look like this, but there are 2 very, very important properties that I want to go over before we move on to anything else with line integrals. So that, again, I can hopefully make a point and show you guys how important these 2 properties are. Now, first things first, with this first example, C is going to be the straight line from my origin, 0, 0, to the ordered pair, 1, 1. That is my curve C. Straight line C. Curve, doesn't matter. Now, when we're doing our line integrals, I'm going to be integrating over that curve C. Now, sometimes that curve C is going to be given in terms of a vector function, which would be the variable t. We don't necessarily need to do that here, but in general, this is actually going to be given in terms of a vector function, r of t, or r hat of t. And we could actually find that vector function here too, but it's not necessary. And then we have a function of 2 variables, x's and y. So again, we started with t, then there's an x, then there's a y. So now we have 3 variables and parameters, and then everything is in terms of ds, so that's a 4th. So now we have 4 variables or 4 parameters for this just one problem. And there's only one integral. Only one integral, which means I got to take those 4 variables and parameters and somehow find a way to write them all in terms of just 1. And there's not necessarily just one way to do this. And that's what I'm going to try to show with these first 2 examples, is that there's not just one way to calculate these line integrals. Alright, we can do this with respect to different choices. I can choose the t, or I can choose the x, or the y, or I can choose the s, and I should get the same exact answer no matter what. And understanding what the easiest choice is going to be, well, that should make your problem quite a bit easier too. But let's start off with this first one, and we're going to try to keep it in terms of that s. We're going to keep it in terms of our arc length. So, first things first, is if I want to do this in terms of arc length, my limits of integration are going to be in terms of arc length. So, well, first of all, my arc length has got to start at 0, because, well, of course, right? I'm starting at the beginning of my curve, right? So I'm starting here, the curve hasn't moved, so I'm starting at 0, and then I'm ending here. Except I got to figure out, well, what is that? What is the total length of my curve here? What is the total arc length of this curve C? So what we're going to do In this case, right triangle trig is going to be our best friend. Make a quick right triangle out of it. We know that the total length on the bottom is 1. The total length on that side on the right is 1, which means my hypotenuse, which is my arc length, quick Pythagorean theorem, root 2. And that'll be the total from there to there. All right. So I'm going to be integrating from 0 to root 2. So now comes the next challenge. How do I get rid of the x's and y's? All right. Well, what we're going to do here is we're going to use the property of similar triangles from geometry, or right triangle trig. And so similar triangles, basically what I'm going to do is I'm going to try to consider this angle here, and kind of keep that angle consistent, and make two right triangles that share that angle in common. So we have our first right triangle, the whole big one, right, that we just figured out. And now I'm going to make a smaller right triangle on the inside. Well, this distance is x, right? However far I made it. This distance is y. And then this distance along my hypotenuse is s. It's my arc length. It's however far I traveled, right? Considering whatever that ordered pair x, y might have been. So I make my two right triangles here. And with right triangles, or actually with any similar triangles, the ratios of the sides are going to have to be the same. And so let's set it up first. Let's do the ratio of, how about the adjacent side to the hypotenuse. Let's start off with that one. Now it's a right triangle, so I can actually use the cosine function. If it makes you feel a little bit better, sure, we'll make that cosine, right? That's my adjacent over hypotenuse. Although you don't necessarily need that to do to do these similar triangles here. So the adjacent to the hypotenuse. Well, on my little triangle, the one that I just made, my adjacent side is x. My hypotenuse is s. And that ratio's got to be the same as my big triangle. Where my big triangle, that adjacent side was 1. And the hypotenuse is root 2. And now I can use this ratio to actually go ahead and figure out, well, what is x going to be? If I get x by itself, and now I have my variable s and just two constants, I'll got to be able to get x in terms of s. And this one's going to be pretty simple, because to get x by itself, just multiply by s on both sides, so the s's cancel there. So x is going to equal s over root 2. So, replace my x with s over root 2. And now I got to substitute for y. Well, I'm going to use the exact same argument over again. Like I said, don't worry about writing all this down. Just try to follow. And now, instead of the adjacent side, how about we do the opposite side? So instead of x, this is y, but everything else stays the same. So it looks like y is actually going to be the exact same thing, which should make sense, right? This is an isosceles triangle. I have a 45, 45, 90. Those two sides have got to be the same no matter what. So y is going to be s over root 2, and then ds. Now, my bounds are in terms of s. My function is just in terms of s, and I'm integrating with respect to s. Everything matches. Once everything matches, I can actually go ahead and do the calculus part of this. So the challenging part is actually going to be these parameterizations. The challenging part is trying to actually set this up so that you get an integral you can actually evaluate. And then hopefully once you get that integral, then the integration is easy, most of the time. So let's actually take this integral then. So I have s over root 2 plus s over root 2. And I'm actually going to step aside, do a tiny bit of scratch work over here. Well, s over root 2 plus s over root 2. So I have 2 s over root 2's. Let's actually rationalize this denominator, right? Let's actually rationalize this to make it a little bit nicer. So multiply by root 2 over root 2. So that means on the top, I have 2 root 2, and then my s. On the bottom, root 2 times root 2 is, what is 2? So those are actually going to cancel. So I can actually simplify when I'm integrating, make it a little bit nicer, as root 2 s. Root 2 is a constant. So you know what? Let's pull the root 2 outside, my limits of integration. And I'm integrating from 0 to root 2, and then it's just s ds. Oh. About as simple as an integral as you're going to see in Calc 3, right? So keep that constant root 2 on the outside. What is the antiderivative of s with respect to s? 1/2 s squared. My limits of integration are from 0 to root 2. So let's plug in our limits of integration. So root 2 times 1/2 times. So if I plug in my upper limit, so that's root 2 squared minus 0 squared. Of course, the 0 is going to go away. But what's root 2 squared? Root 2 squared, those are going to cancel. So it's just 2. Well, what's 1/2 times 2? Those are going to cancel as well. And it looks like the answer to this problem is just going to be root 2. And again, every time we do these line integrals, we should end up with just a constant as our answer. And in this case, we kept everything in terms of s, tried to write everything in terms of the arc length, set up an integral, and we got the result, root 2. Now, let's try that example over again, except let's do it not in terms of s. Alright, now let's try the same problem again, except let's try to do this in terms of x. That means I'm going to get rid of everything else except for x. Now, that means I get to leave this alone, basically. And I got to figure out, well, how am I going to get rid of the rest of it? So, in terms of x, let's worry about my limits of integration first. So, from here to here, well, that's going from 0 to 1, right? Well, that means my new limits of integration are going to be from 0 to 1. X is, just x. That's easy, isn't it? Alright, but what about y? Well, what's y going to become? So now I need to figure out what's the relationship between x and y on my curve C. Except, well, what's the equation of this line? Well, the equation of this line is just going to be y equals x, right? Through the origin, through the ordered pair 1, 1, yeah, that is absolutely going to be the line defined by y equals x. So what does y equal? X. So everything's been really simple so far. Now, what about that ds? What am I going to do with that ds? Well, now we go back to the Pythagorean theorem, the distance formula. We defined what ds was back when we did arc length. We know that ds squared equals dx squared plus dy squared, right? That's my Pythagorean theorem. And I want to get dx now, but this is my relationship. So the first thing is, well, we know x and y, well, y equals x. Well, if y equals x, then dy also equals dx. So, alright, so this becomes dx, and I have two of those. So 2dx's squared equals my ds. So divide by 2, take the square root, and it looks like, well, the square root and the squared cancels, so ds over root 2 equals dx. Alright, so now I know what dx is, but I got to substitute, right? I got to get rid of ds. So a tiny little bit of algebra. I need to, well, basically just multiply that other side by the root 2. Right? Does that make sense? Get rid of the fraction. We're making substitutions. It's just like we did U substitutions way back in Calc 1, and then again in Calc 2, and we've been doing it in Calc 3 as well. So, yeah, we should be fairly comfortable with our U subs, I think. Alright. So, I get that constant of root 2, so it's a constant. Again, I'll pull that outside my limits of integration. So integrating root 2 from 0 to 1 of x plus x, well, that's going to be 2x dx. And now, integrate. What's the antiderivative of 2x with respect to x? X squared. So root 2 times x squared, evaluated from 0 to 1. So we get root 2 times 1 squared minus 0 squared. And that's about as easy as it gets. My answer is just root 2. The same exact answer I got before. And so it doesn't matter if we parameterize in terms of s or x, we should get the exact same thing. Alright, time for example number 3. So for this example, again, we're still using the same function, x plus y, except now my curve is going to be the straight line from the origin horizontally along my x-axis to the point 1, 0, and then vertically up to the ordered pair 1, 1. Now, what we're going to have to do here is actually split this curve up into two separate curves. Basically, we want two piecewise smooth curves. So instead of saying the whole thing is C, I want to break this up into C1 and C2. And I'm going to need to do each part separately, which means this integral is actually going to be rewritten integrating over C1 of x plus y ds, plus I'm going to have to integrate over C2 of my function x plus y ds. And again, that's going to happen quite a bit. We have to sometimes take these curves and break them up into smaller chunks and do each part separately, but we are absolutely going to be able to sum them at the end. So let's start off with C1. So C1 is vertical line from here to here. And again, we got to figure out how am I going to actually, well, make these substitutions. How am I going to try to turn this into just one particular variable? Well, for C1, the nice part is, well, from here to here, let's keep it in terms of s, I guess, for this one. My arc length is s, and it goes from 0 to 1. So I'm integrating from 0 to 1. X, well, x is going from 0 to 1. In fact, in this case, my arc length is just the same thing as my variable x. I'm just counting over. So x is just s plus, well, what's y? Well, along this entire line from 0, 0 to 1, 0, y is just going to be 0. So again, if I understand my curve, I can make my substitutions, and that becomes easy. Well, yeah, so, yeah, from, yeah, y is just 0. Piece of cake. So plus 0, why even do that? So it's ds. About the simplest integral we're going to do today. Antiderivative of s with respect to s is still 1/2 s squared. So 1/2 s squared, evaluated from 0 to 1. I don't even really feel like writing that out. You know it's 1/2, right? It's, yeah. If you need to pause and verify, but yeah. Alright. So it's 1/2. Now let's do the second part. So now I need to integrate over my second curve. Well, my second curve is going just straight up. My second curve is only moving in the y direction. So again, I can keep this in terms of s, or y really, I guess. But in this case, y is the same thing as my variable s. So, alright, let's plug it in that way. So going from 0 to 1, again, looking at that y variable. So I'm integrating from 0 to 1. X is, well, in this case, my x doesn't change. If it's that vertical line up and down, x is always equal to 1. So x becomes 1 plus y. Well, we just said that y and s are the same thing because it's that vertical line. ds. Alright. So the antiderivative of 1 is s. The antiderivative of s is 1/2 s squared. We're evaluating the entire thing from 0 to 1. And so, if I plug in 1, I get 1 plus 1/2, 1 squared, minus, the whole thing will become 0, so plus 1.5, so plus 3/2. 1/2 plus 3/2, 4/2, or just 2. So again, I might have to parameterize my curve and actually separate and break it up. Again, that's nothing new, right? We've done that before in calculus. And again, I parameterized each of these, and when they're straight lines, right? well, not just straight lines, but horizontal lines and vertical lines. And because very easy to parameterize because, again, y is a constant for horizontal lines, x is a constant for vertical lines, and it does make those substitutions a bit easier here. But what I really want to point out is notice I got the answer 2. Now, it was the same function, and I actually had the same starting point and the same ending point, right? Both of these started at the origin 0, 0. Both of them ended at the ordered pair 1, 1, right? Actually, I shouldn't say both. All 3 examples, right? Those first 3 examples all started here, ended here, except when I took a different path, I got a different answer. And that is going to be critical. That is the really important thing that I wanted to actually get across with this example, is that, I mean, not only do I have to break things up, but the path that I take is going to matter. All right? It's not just going to be the endpoints always. It's going to matter the path I travel to get there. And whether I traveled in a straight line or whether I traveled around the outside, I'm going to get a different result. And hopefully that's kind of intuitive because I'm taking a different way to get there. So, well, yeah, things we're going to be a little bit differently, right? The whole idea is that I'm plugging in every ordered pair along my path into this function. So I'm using an entirely different set of ordered pairs here, right? Going over and up than when I did straight there, so I am going to end up with a different result. So again, with these 3 examples, again, like I said, don't worry about necessarily like trying to write it out and make sure you can do these ways. This is typically not how we're going to set these up. But again, I wanted to point out those 2 really, really, really important ideas. The first idea for the first 2 examples is that there's more than one way to parameterize a curve. There's not just one right answer, which means the only way to guarantee you're going to get a problem wrong is to do nothing. All right? So just try things. Try to parameterize in terms of different variables. And if it doesn't work, all right, it might not work. Try something else. Or there might be multiple ways to go about and do it. The second really, really important thing is that the path is going to matter. You got to make sure you draw that curve C every single time. All right, so let's get back to a little bit of the theory and, well, how do we actually write out line integrals in other ways.
So the path of our line integral matters. Now, when I say the path, that's really just another way of describing our curve C and what direction we're traveling along our curve C. And so sometimes, even though these are called line integrals, very rarely are we actually integrating over a line. It would probably be much more appropriate to actually call these curve integrals, or in fact, they actually are referred to as path integrals in, well, some mathematics textbooks. Going back to the other important thing, like I said, typically when we set up these line integrals, there's going to be 4 variables or parameters to start with. Typically t and s, which have to do with our curve, C, or that path, and then x and y, which are going to depend upon our function that we're trying to evaluate along our path. So to evaluate a line integral, the first step really is going to be to parameterize everything in terms of just that one variable or that one parameter. And although there's going to be multiple ways to parameterize, most commonly we're going to parameterize based on that curve C, and typically that curve C is going to be given by a vector function, r of t, which means we're typically going to try to parameterize in terms of t. So let's talk about how we can kind of generalize that process for other examples. The first thing we need to do is kind of recall back from when we talked about arc length, that we had this relationship that for a vector function, that arc length, which is just summing up all those ds's along my curve, C, can be given with this notation, where it's the magnitude of r prime of t dt. And again, just to reiterate, in 2 dimensions, that magnitude of r prime of t dt is, again, using the distance formula, right? Using that magnitude formula, or the Pythagorean theorem formula, where it's the square root of dx quantity squared plus dy quantity squared. So in general, when we reparameterize our line integral in terms of t, this is what it's going to look like. And these are the substitutions we're going to make. Basically, my function that was a function of x and y, I need to replace the x's with what my component function is in the x component for my curve C. And I need to replace y with what my, well, component function is going to be in the y component from my curve C. Again, we're plugging in only the ordered pairs along this path, and so this parameterization is absolutely going to be valid. We're just going to make those substitutions for x and y in terms of some function of t. And then the other part is that we need to substitute for ds. And ds, we're just going to use that substitution that we just talked about a second ago, where we're going to have to find, well, that whole big value there, right, using the magnitude. Now, what this means is that there are three different ways that we can actually write our line integrals at this point. And these are actually only the first three ways. We're going to talk about, well, probably like 8 different ways to write line integrals, but we have those first two that we just wrote out, and then that last one at the bottom, well, x of t and y of t, that's exactly defined by my vector function, right? R hat of t, right? It's those components. So we're really evaluating my function f along that vector function. And then, again, by definition, basically that whole square root part is just the magnitude of r prime of t dt. All right, so let's take a look at an example where we're going to parameterize in this exact same way.
All right, for this example, we're going to actually try to parameterize our entire line integral in terms of t. And this is typically how we're going to parameterize almost all of our line integrals. Typically, we parameterize in terms of t more often than anything else, because we're going to parameterize basically in terms of how we describe our curve C. And how can we describe our curve C as a vector function of t, a vector function r of t. So for this example, again, we have my integral over my curve C, in this case xy squared ds, and we want to be able to substitute every single piece of this to make it in terms of t. And how we're going to substitute that goes back to understanding my curve that I'm actually integrating over. So the curve C that I'm integrating over is the x squared plus y squared equals 9. So that's a circle of radius 3, centered on my origin. And we want just the right half of my circle, so just over here where the x values are positive. And the orientation, right, the direction that my curve is traveling is counterclockwise, which means my arrow is going in that direction. Now, how am I going to parameterize this in terms of just one variable t? Well, actually, what we're going to do here is basically use polar coordinates. If I see a circle, think polar coordinates. Except instead of theta, we're going to use t instead of theta. Although, honestly, we could actually do this problem in terms of theta, and it's not going to make a difference at the end anyway. It's just that, again, typically we're going to use t. So, when I see this circle, polar coordinates tells me that x is equal to r cosine of t, or theta, but in this case, t. So x equals r cosine t. Well, what's my radius here? Well, my radius is 3, right? It's x squared plus y squared equals 9, which is my radius squared, so yeah, my radius has got to be 3. So in this case, looks like my parameterization. X is going to be equal to 3 cosine of t. And similarly, hopefully we're comfortable with this, y is then going to be 3 sine t. So this gives me my first parameterization, the first part. How am I going to substitute for x and y? Boom. And that's going to go right here. But I need to do the rest. I'm going to have to substitute for ds, and I'm also going to have to find my bounds of integration. So let's do ds next. So here's my x and my y. Well, what's ds going to be? Well, from that, what we just showed a second ago, ds is equal to the square root of dx squared plus dy squared dt. Right? Or actually, I should probably put the dt's, right? Should be thorough. Alright. Which means I need to find the derivatives here. So ds is equal to the square root of, well, dx So what is the derivative of x with respect to t? Well, the derivative of cosine is negative sine. So we're going to get negative 3 sine t, quantity squared, plus dy. What's the derivative of 3 sine t? Derivative of sine is cosine, so plus 3 cosine t, quantity squared. Now we just need to try to clean this up a little bit. And again, circles make this quite a bit nicer. So I should put my dt at the end. There. So this is going to become 9 sine squared t plus 9 cosine squared t. And then my dt. 9 and 9. Factor the 9. So square root of 9 times the quantity sine squared t plus cosine squared t dt. But what's sine squared plus cosine squared? 1. That's my most important trig identity. That's going to be 1. So it's just the square root of 9, which is 3. So it looks like my ds up here, ds is going to be just 3 dt. Alright, so let's start making those substitutions, except I still have to do my bounds, right? If I want to rewrite my integral, the first step is going to be, alright, got to rewrite these bounds in terms of t. So going back, so again, t is the equivalent to my angle theta, so what would my angles be at these 2 points? So my starting point, and what's the angle down here on my y-axis? Well, typically we would write 3 pi over 2. And my upper bound would be pi over 2. Except this is going to kind of be an issue because I can't start at 3 pi over 2 and end at pi over 2. That doesn't make a ton of sense. I wouldn't start at the bigger number and then somehow get smaller. So just be careful. We need to make sure that our problem actually makes sense when we set up our parameterizations as well. So instead of using 3 pi over 2, I need to use the coterminal angle negative pi over 2. And again, that way my limits of integration should hopefully make a bit of sense. So I'm going to integrate from negative pi over 2 to pi over 2. Those are my new bounds for my integration. Substitute for x. So that's 3 cosine t. Substitute for y squared. So that's going to be, if I square that, 9 sine squared t. And then my ds becomes 3 dt. And let's clean this up before we actually go ahead and integrate. Erase some of this. Whoops. There we go. Saved it, right? Alright, so let's factor out our constants first. So 3 times 9 times 3. 3 times 9 is 27. 27 times 3, so 81. Factor out that 81. Integrating. Again, if I get rid of this, this, and this, I have a cosine, I have a sine squared. How am I going to actually integrate this? Well, let's do u sub. So, u sub. My u is going to be sine t. So du is cosine t dt, and boom, that'll be a real nice substitution right there. And let's also change our limits of integration as well. Let's do a u sub on that. So if t was negative pi over 2, my lower limit, u is going to equal, well, if I plug in negative pi over 2, sine of negative pi over 2, negative 1. And if t was positive pi over 2, u is going to be 1. Sine of pi over 2 is 1. Alright, so now I'm integrating from negative 1 to 1. I have u squared du. And hopefully this is, again, a very simple integral. And that's the key, right? How can I parameterize? How can I turn this whole thing into something that is manageable? Alright, so let's just finish this up real quick. So 81, the antiderivative of u squared is going to be 1/3 u cubed. We're evaluating from -1 to 1. I can get up my constants a little bit. 81 divided by 3 is 27. So I'm going to get 27 times. And I'm pulling in my limits of integration. So 1 cubed minus -1 cubed. Well, 1 cubed is 1. -1 cubed is -1. So 1 minus -1 is 2. So I have 27 times 2. Well, my answer is 54. And that's the answer to this particular line integral. Now again, if you need to, go back, start the problem over again, try to follow it again. It might even be a good idea, right? When I do some of these examples, just watch it the first time, and then the second time try to actually copy and follow it through. And hopefully we did okay with this. If not, let me know, and I can certainly try to explain it a little bit more. But now we're going to move on to the other way that we look at line integrals, and in fact, the most common way that we're going to do, which is going to involve calculating the physics concept of work. So let's talk about work for a second.
Now, work is found by finding the product of force and distance. But this is only going to be true if the force being applied is in the same direction as our distance is being measured. Otherwise, we're going to have to consider components. So what I mean, for example, is consider you're pulling a box along the ground using a rope that's tied to that box, and your distance is being measured as a vector as well. Our vector for distance is going to be measured horizontally here, right, as the box slides along the floor. But the force you're applying on the box is going to be at an angle because you're kind of pulling slightly upwards. This means that not all of the force you're exerting on the box is actually being applied in that direction of distance. So to find out how much force is actually being applied in the same direction as distance, we're finding that component, and we're going to use a little bit of, well, right triangle trig. So if we draw our right triangle on there, hopefully we can see without too much difficulty that if I pick my angle theta there to be the angle between my force and my distance, then clearly the adjacent side is going to be the component that I want. And a tiny bit of right triangle trig, right? Cosine is obviously the adjacent over the hypotenuse, and so our adjacent side of this triangle becomes the magnitude of force times the cosine of theta. So clearly then work is going to be the product of force, which is actually the magnitude of force times cosine of theta, times the magnitude of the distance. So again, work equals the force times the distance. This gives us our formula here, where work is the magnitude of force cosine theta times the magnitude of distance, but we can rearrange this. Let's put those two magnitudes together. So we have the magnitude of force and the magnitude of distance together at the beginning, but this should look familiar because this is exactly our definition of the dot product from section 12.3. So work is actually going to be calculated as the dot product of the force vector times the distance vector. Now we're ready to talk about the context in which we are going to calculate most of our line integrals in our Calc 3 course. And that's going to be calculating our line integrals of vector fields. So consider a curve C that's passing through our vector field F. Now what is going to be the total work done on that curve by that vector field? So again, remember that vector field is going to apply a force at every single ordered pair in the plane, which means it's going to apply a force at every single point on this curve. And I want to figure out, as I travel from point A to point B, what is going to be the total work done on the force field over that distance, over that arc length of my curve. So, well, let's consider what happens at just one of those individual points. So let's kind of zoom in on that point P. When I look closely at that point P, obviously I have my vector force being applied at that point. And what I'm going to have to consider is going to be the tangent vector, or in this case, the unit tangent vector at that point as well. Clearly, we can see that the force being applied at that point is not in the same direction as my curve. We use that unit tangent vector to describe again, the direction of my curve, right? What's that distance? So we're going to have to use the component. And it's the same component that we just talked about, well, with work, which means the component in that direction of my tangent vector is going to actually be the magnitude of the force times cosine theta. It's that adjacent side. Now here's the cool part. We know that by definition, the magnitude of the unit tangent vector is 1. So it doesn't make a difference to multiply by 1. So that force being applied is going to be, again, the magnitude of force times cosine theta. And let's actually multiply by the magnitude of my unit tangent vector, since that's just 1. Well, then hopefully we can clearly see, just like we did before, that this is going to be the definition of the dot product. So it turns out that the force being applied at that one point is just going to be the dot product of the force and my unit tangent vector, or f hat dot t hat. Well, then to find the total amount of work done, well, it's the product of force and distance. And our distance is our ds, so we're going to multiply our force, the dot product, times our ds, and then sum over the entire curve, which gives us our integral c. And there's our definition for our line integral, which is actually computing the work done. Now, before we get any further, I want to just, again, recap. Going back to section 12.3, remember, our dot products can be negative. So you may calculate the work done and actually end up with a negative value as your answer. Because remember, if we have an acute angle between two vectors, and I'm using vectors v and vectors w here, if that angle is acute, my component is positive. However, if the angle between v and w is obtuse, then my component is going to be negative, because my component is actually going to lie in the opposite direction of the vector I'm computing the component along. Now, the nice part is you don't even really have to worry about this. When we do our calculations, it's all going to be taken care of for us because it comes directly from our dot product theorem. We know that if, again, here's my dot product theorem, v dot w is the magnitude of v times the magnitude of w times cosine of theta. And if the angle between those two vectors, right, if that angle theta is between 0 and pi over 2, well, we know that in quadrant 1, cosine is positive, right? Now, if it was between pi over 2 and pi, right, if that angle between them was now obtuse, now I'm in my second quadrant, cosine is going to be negative. And that's where I'm going to get that, that negative work possibly coming out of my integral. And of course, if theta equals pi over 2, cosine is 0, right? That's when we have perpendicular vectors. So if our vectors are perpendicular, then the work done is going to be 0. So kind of summarizing, just generalized over our entire curve, if the angle between our tangent vector and our force, right, or our vector field describing force, if that is acute at all points on my curve, then my integral for work must be positive. But if the angle between them is obtuse, then clearly my calculation for work is going to end up being negative. Now, this gives us our first definition for work. And this is actually kind of the basis of all the other line integrals we're going to talk about and start writing out. This is kind of the starting point. Our basic line integral of a vector field is going to be integrating over a curve of the dot product of that vector field and the unit tangent in terms of ds. But if we remember from our previous lectures, the unit tangent vector is really our first derivative divided by the magnitude of the first derivative. That's what turns it into a unit tangent. And we also said from earlier that ds is the magnitude of my first derivative, dt. So if I make those substitutions, again, I'm just replacing my unit tangent with the first derivative divided by the magnitude of the first derivative. And if I replace ds with the magnitude of the first derivative times dt, well, what's going to happen here? Hopefully we can see that I have that magnitude of my first derivative in the denominator and also outside, which means they're going to cancel. Which means the, again, kind of procedural formula for the line integral of a vector field is going to be given by this, as that dot product of my vector field and the first derivative of my vector function with respect to t, so the dt. This is the procedural formula, and probably the one that, again, we want to really remember this, because this is how we're going to solve most of our line integrals in a practical manner. Now, however, this is not really the most common way that we write our line integral. Typically what we do is we take that r prime of t dt, and I can actually combine that and make it more compact and write it as just dr hat. Right? It's the derivative of my vector function. So it's dr. And this, put the stars around it, put the box around it, this is probably the most common way that we represent our line integrals. All right, this is pretty much how every example in your textbook and every example in the homework is going to be written. So just make sure you know that when you see that, kind of work backwards that one step to find r prime of t dt. Now, starting again with that dot product of my vector field and r prime of t dt, there are other ways that we can write out our line integral. First of all, if our curve C is given by my vector function r of t, and again we have our bounds for t, well, we're calculating our force, right? We're calculating our vector field only over that curve. That's what integrating over the curve means. So that means that my f hat, my vector field, I'm only evaluating that at my vector curve. So I can actually write f of my vector function r. And again, it's just a kind of a nice notation that lets us state very clearly what it is we're actually calculating. And also, it lets us plug in our actual limits of integration that we're going to use to calculate this integral later on. So again, this is more of a computational formula that's kind of useful for, again, telling us exactly what we're doing if we know that our curve C is given as a vector function. Time for the other way that we write this. So in 2 dimensions, let's say our vector field is given by pi hat plus qj hat. And then our vector function r is, well, given by xi hat yj hat, which means r prime dt is actually going to be dx in the I hat direction, dy in the j hat direction. And we're computing the dot product. So we know how to compute dot products. Find the corresponding components, so p and dx, and q and dy, the corresponding components, multiply them, find their product, and then sum them. And so the most simple way we can actually write this is that our line integral over the curve C is p dx plus q dy. This is another incredibly common way to write out our line integral of a vector field. And we are going to use this actually as quite a bit as well. Maybe not as frequently as the other notation, but this would probably be the silver medal. This is second place for how we represent these vector fields. Now, if my vector field was in 3 dimensions, well, then we have to tack on a plus r dz, but it follows the same argument, so should feel fairly natural. But these are our 2 most common notations for writing out our vector fields, or how we kind of phrase our problems. They're the most compact way, and they are also sometimes the most informative way in what's actually going on. But that means now that we have our 3 ways that we wrote our general line integrals from before, and now we have, well, several other ways that we write our line integrals of vector fields, which we talked about. Now, admittedly, the second to last one, I kind of combined those 2 ideas and wrote it out with a little bit more notation. Again, we don't typically write it that way, but again, it gives you kind of an idea of how we'd actually use it. And this is also an example of why line integrals can be kind of confusing. We have all these different notation, in this case, 8 different notations that really all represent the same idea. So with this section, you really have to make sure you take some time and become comfortable with the notation and the various ways that we write out our line integrals. But now let's try to wrap up with 3 more examples. Back to the chalkboard.
All right, for our first example, we have pretty straightforward, trying to take a line integral. And we're given our function for our vector field, f, and we're given our curve as a parameterized curve in terms of t as a function r of t, so our vector function. So again, we have our vector field and our vector function that is traveling through this field. Now, there's really two things we need to do to try to set up this integral so we can actually evaluate it. We need to parameterize f, put it in terms of the same variable, and we need to take the derivative of r, because, again, we're going to need that dr over there. So how am I going to parameterize f so that everything's in terms of the same variable? Well, the easiest thing to do is, well, to use your curve. We're going to be evaluating this vector field only at points on my curve given by r. And, well, the way this is set up, here's my x component, right? My function for x is that t cubed. My function for y is t squared. And there's my parameterization. There's my x, there's my y. All I need to do now is plug that back into f. So f equals, well, x, y squared. So I need x, that's really t cubed, and then y squared. But y is really t squared. So t squared squared. So that'll be in my I hat direction. And then for the j hat direction, that's going to be minus x squared. So minus, and then, well, x was t cubed, so minus t cubed quantity squared in my j hat component. There's my parameterization. That's it. That's all we had to do. Now my vector field, f, is in terms of t. Although, let's clean this up just a little bit more. So f is equal to, so I have t cubed and t squared squared. Well, t squared squared is t to the fourth. T to the fourth and t to the third is t to the seventh. And again, at this point, if you want to pause and try to figure it out yourself, go for it. But t to the seventh in the I hat component, and then minus, and t cubed squared is really t to the sixth in my j hat component. So again, so that's the first part. We needed to parameterize f, right? And we did. Boom. The next part is to take the derivative of r. You have to find out what is r prime of t going to be. But this is pretty simple too. We're just going to go through component by component. What's the derivative of t cubed with respect to t? 3t squared. So 3t squared in the I hat component. And plus, all right, now take the derivative here. The derivative of t squared is 2t. So plus 2t in my j hat component. And now we have the two pieces that we need. Now I'm going to take these two pieces and find their dot product. And that's what's getting plugged into my integral. So I don't put everything in terms of t. I can put in my bounds as well. We're going from 0 to 1. And then f dot dr. So that means multiply the corresponding components and then sum. So let's see, my corresponding components. So I have t to the 7 and 3t squared as my x components. So multiply t to the 7th times 3t squared. So that's going to be 3t to the 9th. Multiply my y components. So t to the 6th and 2t. I multiply those together. Minus t to the 6th. Minus 2t to the 7th. My dt at the end, and there we go. Now I have a very simple polynomial antiderivative to take with very simple bounds. So again, feel free to pause and see if you get the right answer and check with me, but I'm just going to go ahead and kind of plow right through and actually take this antiderivative. So starting with the first one, t to the 9th, so I got to add 1 to the exponent, so it becomes t to the 10th. Divide by that new exponent 10, so 3/10 t to the 10th, minus, add 1 to the exponent, so it gives me t to the 8th, and divide by that 8. So 2 over 8, all right, that's really going to be a quarter. Now we're evaluating from 0 to 1. All right, really, really nice balance here to actually evaluate this, because when I plug this in, 3/10 minus 1/4 minus 0. Right, from plugging in 0, so I don't really care about that. And then I just got to kind of clean this up. So let's see. If I want to get a common denominator of 20, so 6 over 20 minus 5 over 20. And so that just leaves me with 1 over 20. The answer to my first line integral here is 1 over 20. Example number 2. Again, we're looking at a line integral, our typical way that we represent our line integral. And in this case, our function f for our vector field is given in component form as e to the x, comma, 0. And c is our curve defined by x equals y cubed from -1, -1 to 1, 1. All right. Now, there are, of course, a couple of ways we could go about doing this one, but as soon as I look at my vector field, and I realize that my vector field is actually applying no force in the y component. All the force has to be coming in the x component. There's no force in the y component. I'm actually going to take this notation, and I'm actually going to use the other way that we write out our line integrals, which is integrating over the curve C, where we use p dx plus q dy. Because, well, again, when I look at my function f, remember, this is my p, right? My x component is p. Q is my component for y. And when I plug this in here, well, what happens if I plug in a 0? That just goes away. That's going to be 0. So I'm literally just left with that first part. So if I plug that in, p is e to the x. So e to the x dx. And I actually got really lucky with this one, because my component in the x direction is only in terms of x, which means I can actually integrate this. I don't have to do any other parameterizations. All my variables match. The only thing left to do is make sure that my bounds now are also going to be in terms of x. Well, my bounds, I know what my bounds are going to be in terms of x, from -1 to 1. That's what the ordered pair said. So I'm integrating from -1 to 1. Piece of cake there. And, yeah, now a very simple integration. Because what's the antiderivative of e to the x? E to the x. You're evaluating from -1 to 1. So I plug in my upper limit of integration. E to the 1 is just e. Minus my lower limit of integration is -1. E to the -1 is really 1 over e. And we're done. There's my answer. I didn't have to do anything else. I didn't have to make my life any harder than it needed to be, because I understood what was going on. And I understood the different notations and when one might be more useful than the other. Now, let's say you didn't realize that. Let's say you didn't notice that you could do the problem this way, and you were trying to just, well, start with trying to parameterize this curve. So that's actually typically the best way to kind of start any problem, is try to understand the curve, and try to come up with a parameterization. So I do want to go through real quick how I would do that with this particular example. So I see that x equals y to the third, and I know that, again, at the end, I want my vector function r hat of t, and I need my x component and my y component, and my x and my y component are going to have to satisfy that relationship, that the x has got to be y cubed, and that means my x component has to be my y component cubed. So how am I going to do that? Well, I'm literally going to choose the easiest way that I possibly can. If I let my y component be t, well then my y component is t, x is y cubed. Well then my x component has got to be whatever the y component cubed is, and that's t cubed. And yeah, there's my parameterization. I was just able to parameterize my curve. R of t equals, well, t cubed, comma, t. But again, probably not the easiest way to do this problem. But again, that's okay. Like I said, you might not choose the right thing. Just choose something and keep trying. And the more you practice, the better your intuition will get for these sorts of things. Let's try our last example. Time for our last example. So again, we're given a typical line integral that we want to compute. We're given that the field that my curve is traveling through is defined by the vector field function with the x squared component in the x direction and xy in my y direction. And my curve C is given by the function x squared plus y squared equals 4 in the counterclockwise direction. And, well, let's start there. Again, typically we want to start with our curve C, understand what that looks like, how we can parameterize that, and then use that parameterization in the rest of the problem. So, let's see. So C, right, we have a circle, radius 2, and we talked about this earlier. So we're parameterizing very similar to how we parameterize polar coordinates. So x equals 2 cosine t. And we do want to use the variable t, right, for our parameter. And y equals 2 sine t. All right. Now that we have my parameterization, I need to use these two things to, again, parameterize f, and then figure out what r prime is going to be also. So I might as well start with f. I have it up here. So f equals, well, x squared. Well, what did I just parameterize as x? 2 cosine t. So I actually want 2 cosine t squared, which is really 4 cosine squared t. And then the xy. Well, I got to multiply x and y. So 2 cosine t times 2 sine t, well, that's going to be 4 cosine t sine t. And there is my parameterized f. Next up, I got to find r prime. Well, I have my x and my y components, so r of t is really 2 cosine t, comma 2 sine t. And so r prime is going to be, take the derivative component by component. The derivative of 2 cosine t, negative 2 sine t. The derivative of 2 sine t, 2 cosine t. And there we go. All right. I have my f parameterized all in terms of my variable t. I have r prime parameterized all in terms of my variable t. So now I can go ahead and compute that dot product and actually plug it back into my integral. So, since I have a little bit of room down here, so my integral, so I'm integrating, I can put my bounds as well. It was the entire circle, so I'm integrating from 0 to 2 pi. And now the dot product. So multiply those corresponding components. So my x components, 4 cosine squared t and negative 2 sine t. Multiply those together, so that's negative 8 cosine squared t sine t plus, and now I need to multiply my y components together. So 4 cosine t sine t times 2 cosine t. So 4 and 2 is 8. I have cosine and cosine, so that's cosine squared t sine t dt. And this is the integral that I want to evaluate. Well, can I simplify it a little bit more first? Well, I have minus 8 cosine squared sine and plus 8 cosine squared sine. What's going to happen there? Well, they're going to cancel each other out, right? Minus 8 plus 8 of the same thing is going to be equal to 0. The answer to this problem is 0. When I calculate that dot product, everything cancels out. That means my dot product was 0. Wait a second. What does it mean if my dot product is 0? Well, back to technology one last time.
Here I've graphed the vector field F, which is obviously the vectors in blue, and our curve C, which is the circle in red, including its orientation. So why did my answer come out as 0? Well, you might already be able to see just from looking at this picture, but I'm going to zoom in just in quadrant 1, and we can take a little bit of a closer look. When I zoomed in quadrant 1, hopefully we can start to see that when I drew in my tangent vectors in green, every single tangent vector is at a right angle to the field at that point. Meaning that, well, we know that when the two vectors are at a right angle, their dot product is going to be 0. And actually, for every single point around this circle, the field is actually going to be at a right angle to the tangent vectors at that point. That's why the whole thing canceled out over the entire curve when we set up our integral. Yeah, take a look now at the bigger picture, and hopefully you can see it too. In every single quadrant, whether the vectors are coming towards the circle or, I guess, heading away from the circle, every single force vector is at a perpendicular angle to my curve, and that's why it's 0.